The speed of light is 299,792,458 meters per second. That number is so large that it is almost impossible to intuitively grasp. In 1 second, light travels 7.5 times around the entire circumference of Earth. In 8 minutes, it crosses the distance from the Sun to us. In a single millisecond, it covers the distance from London to New York. It is the fastest thing in the universe, the absolute limit. The speed barrier that the deepest laws of physics have built into the structure of reality itself. And it is catastrophically, tragically, fundamentally too slow for interstellar travel. Not slightly too slow, not almost fast enough. Catastrophically insufficient. For us, for any alien civilization, for anyone who wants to move meaningfully between the stars. Tonight we are going to work through this honestly, through the specific physics that makes interstellar distances practically impassable. Through the reasons why the speed of light is not a gift, but a prison wall, built not from any particular material, but from the logic of space and time themselves. Through what this means for the possibility of contact with other intelligence in the universe. Through the loneliest fact in all of physics. If the night is long, stay with this. Let us begin with the number that most people have never actually confronted, not in the abstract, but in the specific units that make its scale undeniable. The nearest star to Earth is Proxima Centauri. It is 4.24 light-years away. This means that light, travelling at 299,792 kilometers per second, faster than anything in the universe, takes 4.24 years to get there. Let us convert this to something more tangible. 4.24 light-years is approximately 40 trillion kilometers. 40 trillion kilometers. 40,000 billion. For comparison, the distance from Earth to the Moon is about 384,000 kilometers. The distance to Proxima Centauri is 104 million times larger than that. Not 100 times, not 1,000 times, 104 million times. The fastest spacecraft ever built by human hands, the New Horizons probe at its peak, travels at roughly 57,000 kilometers per hour. At that speed, the journey to Proxima Centauri would take approximately 78,000 years. 78,000 years. This is roughly 3 times longer than the entire span of recorded human civilization. The Egyptian pyramids were built about 4,500 years ago. 78,000 years is 17 times longer than that, and this is to the nearest star. The Milky Way galaxy spans approximately 100,000 light-years in diameter. The nearest large galaxy, Andromeda, sits 2.537 million light-years away. The observable universe extends 46 billion light-years in every direction. The numbers are so large that the mind simply refuses to process them, and that refusal is part of the problem. Our intuitions about distance are calibrated to the scale of a human life, a human journey, a human civilization. The scale of interstellar space exceeds that calibration by so many orders of magnitude that the numbers become essentially meaningless without careful translation. Let us do that translation now. Imagine you wanted to build a scale model of the solar system where Earth was the size of a grain of sand, roughly 1 millimeter in diameter. At this scale, the Moon would be a smaller grain of sand, about 3 centimeters away. The Sun would be a sphere 11 centimeters across, sitting about 11 meters away from your grain of sand Earth. The outer edge of the solar system, roughly where the Voyager probes now travel, would be about 1 kilometer from the Sun. Now, at this same scale, where would Proxima Centauri be? About 3,000 kilometers away, the distance from London to somewhere in the middle of Russia, or from New York to somewhere in the middle of the Pacific Ocean. 3,000 kilometers, in a model where Earth is a grain of sand. That is the gap between stars. Not a large room, not a city, not a country. A gap spanning the width of a continent in a model where our entire planet has been compressed to the size of a grain of sand. This is what interstellar space actually looks like when you run the numbers. And every proposed interstellar mission, every spacecraft, every generation ship, every laser sail probe, must somehow bridge this gap. Now let us talk about why the speed of light is exactly what it is, about where this number comes from and why it cannot simply be exceeded. The speed of light is not merely the speed of photons. It is not a property of one specific kind of radiation that other things could potentially outpace. It is the fundamental speed of causality in the universe, the maximum rate at which any influence, any information, any physical interaction can propagate. In Einstein's special theory of relativity, the speed of light c is not an additional constraint on top of the laws of physics. It is a structural feature of spacetime itself. It defines the relationship between spatial and temporal dimensions. Changing it would be like changing the number of spatial dimensions. It would not be modifying a parameter within physics, but rewriting the framework within which physics operates. What happens when an object with mass attempts to approach the speed of light? Its mass increases. Not metaphorically, physically. The inertial mass of an object grows as its velocity increases. At 90% of the speed of light, the object's effective mass has increased by a factor of about 2.3 relative to its rest mass. At 99% by a factor of 7. At 99.9% by a factor of 22. At 99.99% by a factor of 71. This means that the force required to accelerate the object further must also grow proportionally. The closer to the speed of light, the more energy is required for the next increment of velocity. The relationship is not linear, it is hyperbolic. The required energy approaches infinity as velocity approaches c. To accelerate an object with mass to exactly the speed of light would require an infinite amount of energy. Not a very large amount, infinite. This is not a technological limitation, it is a mathematical consequence of how mass, energy, and velocity relate to one another in our universe. Photons, particles of light, can travel at the speed of light because they have no rest mass. They do not accelerate to the speed of light from rest. They exist only at the speed of light. This is a fundamentally different situation from any object with non-zero rest mass, which must always travel slower than c, regardless of how much energy is applied. This is not the first time in history that a proposed limitation on travel speed turned out to be fundamental rather than technological. Before the steam engine, crossing an ocean was constrained by wind and muscle. Before aviation, altitude was constrained by terrain. But in those cases, the constraints were physical and engineering obstacles that could be engineered around. The speed of light barrier is different in character. It is not an obstacle within the framework of physics. It is a property of the framework itself. Let us now talk about the specific fuel calculation that makes the scale of this problem concrete, the Tsiolkovsky rocket equation applied to relativistic speeds, and what it tells us about what is actually required to travel at even a small fraction of the speed of light. The Tsiolkovsky rocket equation describes how the velocity a rocket can achieve relates to the ratio of its initial mass, full of fuel, to its final mass, empty of fuel. For relativistic speeds, the equation becomes more complex, incorporating the Lorentz factor. But the essential behavior is the same. Achieving higher velocities requires exponentially larger fuel fractions. Let us consider the most optimistic possible scenario. Suppose a civilization, or humanity itself, develops a perfect antimatter rocket engine. Antimatter annihilates with matter, releasing 100% of the combined mass as energy, according to E equals mc squared. This is the highest possible specific impulse achievable by any rocket engine within known physics. Nothing we know of is more energy-dense than matter-antimatter annihilation. What does this best possible engine require to achieve various fractions of the speed of light for a round trip, accelerating to cruise speed, decelerating at the destination, accelerating again for the return trip, and decelerating back home? To reach 10% of the speed of light, fast enough to reach Proxima Centauri in about 42 years, and complete a round trip with full deceleration at both ends, the mass ratio required is roughly 40:1. This means that for every kilogram of useful payload, every kilogram of habitat, science equipment, crew, food and supplies, you need 39 kilograms of antimatter fuel. A crewed vessel with a useful payload of 100 tons would require approximately 3,900 tons of antimatter. For reference, the entire International Space Station masses about 420 tons. And antimatter does not exist in nature in usable quantities. It must be manufactured in particle accelerators. The current world production of antihydrogen, the most advanced antimatter we can produce, amounts to a few dozen nanograms per year across all facilities globally. At this production rate, accumulating 3,900 tons of antimatter would take longer than the current age of the universe, multiplied by roughly 1 trillion. To reach 50% of the speed of light, fast enough to reach Proxima Centauri in about 8.5 years, the mass ratio for a round trip climbs to roughly 100:1. 99% of your launch mass is fuel. To reach 90% of the speed of light, the mass ratio for a round trip becomes roughly 1,600:1. More than 99.9% of launch mass is fuel. For a 100-ton payload, you need 160,000 tons of antimatter, an amount that is, at current production rates, completely beyond the reach of any conceivable near-future civilization. These numbers do not improve with better engineering. They are consequences of the Tsiolkovsky equation applied to relativistic physics. Better engines within known physics cannot overcome them, because the equation describes fundamental limits of propellant-based propulsion regardless of the specific mechanism. And this is for travel to the nearest star. For stars at the typical distance of most stellar systems in the galaxy, tens or hundreds of light years away, the required mass ratios become astronomical in the most literal sense. Now let us talk about time dilation, the aspect of special relativity that sounds like a solution but turns out to be a complication with its own set of profound consequences. Special relativity predicts that time passes more slowly for a moving object than for a stationary observer. This is not an approximation or an artifact of measurement. It is a genuine physical phenomenon with real consequences, confirmed experimentally in countless settings, from atomic clocks flown on aircraft to the extended lifetimes of muon particles produced in the upper atmosphere. The mathematical relationship is expressed through the Lorentz factor gamma equals 1 over the square root of 1 minus v squared over c squared. At 99% of the speed of light, gamma is approximately 7, meaning that for every 7 years that pass on Earth, only 1 year passes for the traveller. At 99.9%, gamma is approximately 22. At 99.99%, gamma is approximately 71. This creates an apparent opportunity for interstellar travel. A crew travelling at 99.99% of the speed of light toward a star 100 light-years away would experience a journey of only about 1.4 years of subjective time. From their perspective, the trip is manageable within a human lifetime. The universe, as perceived aboard the ship, has effectively compressed. But this solution has a fundamental cost. While the traveller experiences 1.4 years, the Earth experiences 100 years. Everyone the traveller knew is dead. The civilization they left has changed beyond recognition. The technology that built the ship may now be obsolete. the mission objectives they departed with may no longer be relevant. Time dilation is not free travel through space. It is travel through space at the cost of time experienced by everything and everyone that does not make the journey. The traveller trades their temporal context, their era, their relationships, their place in the flow of history, for faster, subjective transit. And the return journey doubles this. If the traveller goes to a star 100 light-years away and comes back, Earth experiences 200 years, while the traveller experiences only about 2.8 years. The traveller returns to a world 2 centuries removed from the one they left. This is not merely an emotional complication, it is a civilizational one. A program of interstellar exploration based on relativistic time dilation would produce travellers who are temporally stranded, unable to meaningfully communicate with or contribute to the civilization that sent them, because by the time they return, that civilization is essentially a different civilization. There is also the practical problem of the journey itself at relativistic speeds. At 99.9% of the speed of light, the interstellar medium, the sparse gas and dust that fills the space between stars, averaging roughly 1 atom of hydrogen per cubic centimetre, becomes a storm of energetic particles. From the perspective of the ship, these nearly stationary hydrogen atoms are approaching at near light speed. Their energy in the ship's reference frame is equivalent to high-energy protons in a particle accelerator. Studies suggest that at relativistic speeds, the radiation dose from the interstellar medium would be lethal to unshielded biological organisms within minutes to hours, depending on the specific speed. Adequate shielding is possible in principle, but adds enormous mass, which circles back to the propellant mass ratio problem. And then there is the collision hazard. A grain of sand, roughly a milligram of mass, moving at 99% of the speed of light, carries kinetic energy equivalent to about 44 kilojoules. The energy of a hand grenade. A single such grain of sand hitting the forward surface of a ship travelling at near light speed would be a catastrophic event. The interstellar medium contains dust particles of this size in sufficient density that shielding against them represents a serious engineering problem with no obvious solution at relativistic velocities. Now let us talk about the proposed workarounds, the concepts that come up in every discussion of faster-than-light travel, and address each of them with the level of honesty they deserve. The Alcubierre warp drive. In 1994, physicist Miguel Alcubierre published a paper describing a solution to Einstein's field equations in which a region of spacetime, a bubble, contracts in front of a ship and expands behind it, effectively moving the ship between 2 points faster than light would travel through normal, flat spacetime. The ship itself remains stationary within its local spacetime bubble.
Special relativity is not violated because the ship is not moving through space. The space itself is moving. This is mathematically interesting and physically coherent as a solution to the equations, but it has several problems that are not engineering challenges. They are physical requirements that have no known solution. First, the Alcubierre metric requires negative energy density, exotic matter that has negative mass per unit volume. This is not simply matter we have not yet synthesized. It is matter whose existence is not confirmed by any observation and whose properties are required by the warp drive equations to be so unusual as to border on physically implausible. Second, the amount of negative energy required by the original Alcubierre metric was calculated to be comparable to the total mass energy of Jupiter. Subsequent theoretical work has reduced this estimate, but the fundamental requirement for exotic negative energy matter has not been removed. It has only been quantitatively reduced. Third, the warp bubble, once created, isolates its interior from the external universe.
A ship inside the bubble cannot send any signal to the exterior, cannot communicate, cannot steer, cannot control the bubble from within. The bubble would have to be created and controlled entirely from outside. This makes the practical use of the drive, even if the physics were otherwise favorable, deeply problematic. The Alcubierre drive is not science fiction pretending to be science. It is real mathematics applied to real physics. But it is mathematics describing a hypothetical configuration that requires materials and conditions that may not exist in our universe. The gap between a solution to Einstein's equations and a buildable propulsion system is not an engineering gap. It is a gap in fundamental physics. Wormholes. A traversable wormhole, a tunnel through spacetime connecting two distant points, also appears as a solution in general relativity under certain conditions. The most basic example, the Einstein-Rosen bridge discovered in 1935, is a mathematical feature of the Schwarzschild solution describing the space-time geometry of a black hole. But the Einstein-Rosen bridge is not traversable. The throat collapses faster than any object can pass through it. Traversable wormholes require the same negative energy exotic matter as the Alcubierre drive to hold their throats open against the tendency to collapse. The amount required is again enormous, comparable to a stellar mass worth of exotic matter, though again theoretical work has reduced estimates while not eliminating the requirement. Even if traversable wormholes could be created and held open, the question of creating them at useful locations remains unanswered. A wormhole connecting Earth to Proxima Centauri would be useful. A wormhole connecting Earth to some random point in intergalactic space would not. How to create or position a wormhole at a specific desired location, given that the mechanism for creating it in the first place does not exist, is not a question that current physics can begin to address. Quantum entanglement. This is perhaps the most frequently misunderstood item on the list, because the phenomenon is real and genuinely strange, and the misunderstanding is understandable. Two particles can be prepared in an entangled quantum state, such that measuring one particle instantaneously determines the state of the other, regardless of the distance between them. This has been experimentally confirmed many times and is not in any doubt. It appears to involve an instantaneous correlation across arbitrary distances, but it does not permit communication faster than light. The reason is precise and important. When you measure your entangled particle, you get a random result. The outcome is not under your control. It is determined by quantum probability, not by your choice. Your partner, measuring their entangled particle, also gets a random result. Their result is correlated with yours. If yours was spin up, theirs is spin down. But they cannot know this until they compare results with you through a classical channel, which is limited to the speed of light. There is no way to encode information in the random results of quantum measurements. The correlations are real but uncontrollable, and information requires controllable signals. You cannot transmit a message, cannot choose what the other party receives, using quantum entanglement. This is not a gap in our understanding of quantum mechanics. It is a provable theorem within the framework of quantum mechanics called the no communication theorem. Quantum entanglement creates correlations. It does not create a channel. The distinction is fundamental and cannot be engineered around. Let us now talk about something that is specific, concrete, and currently happening, about what our actual nearest probe to another star looks like in the context of this discussion. Voyager 1 launched in September 1977. It has been travelling away from Earth for nearly half a century. It crossed into interstellar space, beyond the heliopause, the boundary of the Sun's influence, in 2012. It is now approximately 23 billion kilometers from Earth, the most distant human-made object in existence. The radio signal from Voyager 1 takes more than 22 hours to reach Earth. Voyager 1 is travelling at approximately 17 kilometers per second relative to the Sun. This is 0.006% of the speed of light. At this speed, the journey to Proxima Centauri, the nearest star, would take approximately 73,000 years. 73,000 years. Voyager 1 has been flying for nearly 50 years, and it is 0.002% of the way to the nearest star. This is not a criticism of Voyager. Voyager is one of the most extraordinary engineering achievements in human history. It has provided irreplaceable scientific data about the outer solar system and the interstellar medium. It is still operating, still returning data, still making discoveries nearly 5 decades after launch. But in the context of interstellar travel, its position illustrates the scale of the problem with unavoidable clarity. 5 decades of flight in the most distant object we have ever created, and we have barely begun to cross the distance to the star next door. If we accelerated Voyager by a factor of 1,000 to 17,000 kilometers per second, roughly 6% of the speed of light, the journey to Proxima would take about 70 years, one human lifetime. Marginally within the realm of a dedicated multi-generational mission. But the energy required to accelerate Voyager's mass to 6% of the speed of light, not a crewed vessel, just the existing probe, would exceed the total energy output of humanity's current civilization over many years. This is the scale of the problem. Not engineering that needs to be improved, physics that is being confronted. Let us now address the Fermi paradox directly, because it is the most important consequence of everything we have discussed, and it deserves to be stated clearly. In 1950, physicist Enrico Fermi asked a question during a lunch conversation with colleagues at Los Alamos. The specific version attributed to him varies by account, but the essence was this: given the age of the universe, the number of stars, and the apparent likelihood of life, where is everyone? The argument is straightforward. Our galaxy is roughly 13 billion years old. It contains somewhere between 200 and 400 billion stars. A significant fraction of those stars have planets, and a significant fraction of those planets orbit within habitable zones. Life on Earth appeared within a few 100 million years of Earth's formation, suggesting that the conditions for life did not require a particularly long time to be met. Intelligence followed billions of years later, and technology, at least the kind capable of interstellar communication, followed a few 100,000 years after that. By these estimates, even if intelligent life is extraordinarily rare, arising on only 1 in a billion habitable planets, the galaxy should contain thousands of technological civilizations. And even if those civilizations expand slowly, at 1% of the speed of light, which is faster than anything we have built, but far below what is theoretically possible, they would have had time to colonize the entire Milky Way many times over in the galaxy's 13 billion year history. So where are the signs? Where are the radio signals, the megastructures, the von Neumann probes, the altered stellar spectra that would indicate a galaxy-spanning civilization reshaping stars for energy? The silence of the night sky is the Fermi paradox, and the speed of light is one of the most compelling candidate explanations for that silence. If travelling between stars is not merely difficult, but catastrophically, fundamentally expensive in terms of energy and time, if even the most advanced physical civilization is constrained by the same speed limit we face, then the galaxy may be full of life that is simply unable to go anywhere. Each civilization is locked within its home star system or the systems immediately adjacent, with no practical way to make contact with others except by waiting for light-speed signals to cross the void. The silence would not be the silence of absence, it would be the silence of isolation. This is not the only possible explanation for the Fermi paradox. There are many. Life may be genuinely rare, not just intelligent life, but any life, including the microbial kind from which all complex life on Earth descended. The window during which a civilization emits detectable radio signals may be short. Perhaps most civilizations transition to technologies that are harder to detect from a distance. Perhaps civilizations destroy themselves before reaching the level where interstellar signals become practical. Perhaps the signals exist and we simply lack the sensitivity or are searching in the wrong frequency ranges. All of these are serious possibilities.
But the constraint of the speed of light gives the Fermi paradox a different character than it would have in a universe where faster-than-light travel were possible. In a universe with warp drives that actually work, the silence would be almost impossible to explain. A single civilization that cracked FTL travel 1 billion years ago could have filled the observable universe with its presence. The silence would scream. In our actual universe, where the speed of light is what it is, and the fuel requirements for even modest fractions of that speed are what they are, the silence is expected. It is the natural acoustic environment of a universe where everyone is trapped in their own corner, separated by distances that take light years to cross and light years for signals to traverse. The speed of light does not make the Fermi paradox go away, but it provides a framework within which the silence is not paradoxical at all. It is simply physics.
Now let us talk about what the universe looks like from the perspective of a civilization that understands all of this. What the rational response to the speed of light barrier actually is, if you are a species capable of grasping its implications. You cannot reach other stars in any practically meaningful time frame using propellant-based propulsion within known physics. The fuel requirements are prohibitive, the travel times are civilizational in scale. You can, in principle, send small automated probes at significant fractions of the speed of light if you are willing to invest extraordinary amounts of energy and accept decades-long travel times even to the nearest stars. Breakthrough Starshot, the proposal to accelerate gram-scale laser sail probes to 20% of the speed of light using a ground-based laser array, is the most developed real-world concept for this kind of mission. At 20% of the speed of light, a probe would reach Proxima Centauri in about 21 years. The engineering challenges are substantial: keeping the laser array aligned over interstellar distances, building a sail that can withstand the laser power required to accelerate it, fitting meaningful scientific instruments onto a chip-scale probe. But these are engineering challenges, not physics barriers. A gram-scale probe is not a crewed vessel. It cannot carry humans. It cannot be recovered. It flies past the destination and returns data that arrives 21 years after the probe was launched and 4 years after the probe passed the target star because of light travel time. But it is real. The physics works. And it would be the first time in human history that we had actual data about another stellar system from something other than light collected passively by telescopes. If Breakthrough Starshot works, the result is not interstellar travel in the sense most people imagine it. It is interstellar reconnaissance. You learn what is there. You still cannot go there. The information crosses the light years. The people stay behind. This is the honest picture of what interstellar exploration actually looks like within known physics. Not ships full of people arriving at new worlds. Signals crossing the void, probes flying past without stopping, data arriving years or decades after it was collected, already describing a past state of the destination rather than its present. This is not failure, it is what the universe allows. And working with what the universe allows, rather than with what we imagine it should allow, is how genuine discovery happens. Let us now talk about what the next few decades could actually reveal, about the realistic frontier of knowledge about other worlds and potentially other life, within the constraints of the speed of light. The James Webb Space Telescope, currently operational, is analyzing the atmospheres of exoplanets through a technique called transit spectroscopy. When a planet passes in front of its star, starlight filters through the planet's atmosphere. Different molecules absorb different wavelengths. By analyzing the resulting spectrum, astronomers can determine what the atmosphere contains. In 2023, researchers reported a potential detection of dimethyl sulfide, a molecule produced on Earth almost exclusively by marine phytoplankton, in the atmosphere of K2-18b, a planet orbiting in the habitable zone of its star, about 120 light-years away. The finding was reported with extensive caveats. The signal-to-noise ratio was modest, abiotically produced DMS cannot be ruled out, and follow-up observations are required before any conclusion can be drawn. But the detection, if confirmed, would represent the first plausible biosignature in the atmosphere of an exoplanet. The first chemical evidence that the process of life, or something that produces the same chemical products as life, may be occurring on a world orbiting another star. K2-18b is 120 light-years away. A signal from K2-18b sent today would arrive here in 120 years. A response sent now would arrive there in 120 years. A round-trip exchange, the simplest possible dialogue, would take 240 years. A spacecraft travelling at New Horizons speeds would arrive at K2-18b in roughly 2 million years. This is the specific character of what the speed of light means for our relationship to other potentially inhabited worlds. We can see them, we can detect the chemical products of their possible biology. We cannot go there in any time frame that resembles a human lifetime, or even a human civilization. Knowing without being able to go. Seeing without being able to touch. Detecting signs of possible life on a world from which the light has been travelling for 120 years, and knowing that response to any signal we send will take another 120 years to arrive. This is what contact with the broader universe actually looks like. Not a visitation, not an arrival. A very slow, very patient exchange of light across distances that dwarf anything we have names for in ordinary language. The next generation telescopes, the extremely large telescope with its 39-meter primary mirror currently under construction in Chile, the giant Magellan telescope, the planned Habitable Worlds Observatory Space Telescope, will push this capability further. They will be able to characterize the atmospheres of Earth-sized planets in the habitable zones of nearby stars. Proxima b, a planet in the habitable zone of Proxima Centauri, 4.24 light-years away, is among the candidate targets. If the extremely large telescope detects oxygen and methane simultaneously in the atmosphere of Proxima b, that would be one of the most significant scientific findings in human history. Oxygen in the presence of methane is chemically unstable. The two react with each other and are consumed. Maintaining both simultaneously in an atmosphere requires a continuous source. On Earth, that source is life. Photosynthesis produces oxygen. Methanogenic bacteria produce methane. If that detection happens, and it might, within the lifetimes of people currently reading this, we will know that there is life, or something that produces the same chemistry as life, in the star system nearest to ours. The star system whose light we can see on a clear night as a dim red point in the constellation Centaurus, 4 light-years away. And we will not be able to go there in any meaningful time frame. The speed of light gives us eyes. It gives us the ability to receive information from across the cosmos, to read the chemical fingerprints of distant worlds, to know things about the universe far beyond our physical reach. What it does not give us is mobility. The photons come to us. We cannot follow them back. This asymmetry, information flowing freely, matter constrained absolutely, is perhaps the central fact of our relationship to the universe. We live in a universe that is, in principle, fully observable over very long timescales, and almost entirely unreachable. Let us talk about what the constraint of the speed of light actually means for any alien civilization attempting to reach Earth. Not in abstract terms, but in the specific arithmetic of what such a journey would require, step by step, beginning from first principles. Suppose a civilization exists around a star 50 light-years from Earth. This is close by galactic standards. The galaxy spans 100,000 light-years. Most stars are thousands or tens of thousands of light-years away. 50 light-years is a near neighbor, one of perhaps a few hundred stars within that radius. This civilization has observed Earth. Perhaps they detected our oxygen atmosphere through their equivalent of transit spectroscopy. Perhaps they detected our radio emissions, the electromagnetic leakage from our civilization that has been expanding outward as a sphere of radio waves since the early 20th century. The outer edge of that sphere currently sits about 120 light-years from Earth. Any civilization within 120 light-years could, in principle, have detected our radio signatures. So they know we are here. They have decided to send something. What are their options? Option 1, a radio signal. They transmit a signal toward Earth. It travels at the speed of light. It arrives 50 years after transmission. We detect it, decode it, and realize it represents a message from another civilization. This is the most energetically efficient option and the one that the laws of physics most clearly permit. But it is not a visit. No one comes to Earth. No exchange of biology or material culture occurs. Just information, traveling at the maximum allowed speed. Option 2, a small automated probe at relativistic speed. They accelerate a probe to, say, 20% of the speed of light. At this speed, the journey takes 250 years. For the probe to reach 20% of c, it requires an energy input far beyond anything we can currently achieve. But let us grant that a civilization 50 light-years away may have developed the necessary technology. The probe arrives in our solar system 250 years after launch. It begins transmitting. Its signals take 50 years to reach the home civilization. Total round-trip time for any information, 300 years after the probe was sent. What does the probe weigh? If it is a gram-scale laser sail, comparable to breakthrough starshot concepts, the energy required to accelerate it to 20% of the speed of light is on the order of 10 to the 20 power joules, roughly equal to the total energy output of the Sun over about 1/5 of a second. This is a staggering amount of energy to expend on a message, but potentially accessible to a civilization capable of harvesting significant fractions of its star's output. A gram-scale probe carries almost no payload. No biology, no physical artifacts, just sensors and a transmitter, and whatever information can be stored in a chip-scale package. Option 3, a crewed vessel at relativistic speed. They accelerate a ship massive enough to carry crew, life support, supplies, and a means of deceleration. Let us say the useful payload, everything except fuel, is 1,000 metric tons. A modest spacecraft by any measure. To reach 50% of the speed of light and decelerate at both ends, a round trip, requires a fuel-to-payload mass ratio of several hundred to 1, even with perfect antimatter propulsion. The ship would need to carry tens of thousands of metric tons of antimatter, more than 100 times the mass of the Great Pyramid of Giza in antimatter. The journey one way takes 100 years at 50% of the speed of light. Due to time dilation at 50% of c, about 87 years pass for the crew. They age. they experience most of a human lifetime in transit. Their civilization back home has aged 100 years by the time they arrive. Everyone they knew personally is dead or very old. They arrive at Earth. They spend some time here, years, decades. Then they begin the return journey. Another 100 years pass at home, 87 years pass for them. When they return, 200 years have passed at their home civilization since the mission was launched.
The civilization that sent them may no longer exist in recognizable form. The technology that built the ship may be obsolete. The mission objectives they were given may have been superseded by subsequent developments. This is the specific character of crude interstellar travel, even at a substantial fraction of the speed of light. It severs the travelers from their civilization. It makes every mission a one-way cultural journey, even if the physical path eventually returns to the starting point. And this is to a destination 50 light-years away, close by galactic standards. Now let us talk about the specific version of this problem that is most relevant to Earth, about what it would mean for an alien civilization to detect us and decide to respond with a physical visit. The first radio signals from Earth that were powerful and coherent enough to potentially be detected by an alien civilization date to the early 1930s. The Doppler shift of a signal from a moving transmitter, combined with the lack of natural explanation, would mark it as artificial to any civilization with the analytical tools to look for such things. This sphere of detectable radio emission is currently expanding at the speed of light. Its outer edge is now about 90 to 100 light-years from Earth. Any civilization within that radius could have detected our signals. But, and this is crucial, they could not have received the signal, decided to respond with a physical visit, and arrived here yet. Even if they received our first radio signals the moment they were emitted in the 1930s, and immediately began constructing a ship, and launched that ship within a few decades, and travelled at 50% of the speed of light, the earliest such a ship could arrive at Earth is approximately 2130, over 100 years from now. More realistically, if they needed time to analyse the signal, confirm its artificial origin, plan a response mission, construct the necessary hardware and launch, which might easily take a century even for an advanced civilization, the earliest arrival would be 2230 or later. If the civilization is 500 light-years away, still within the galactic neighbourhood on larger scales, they have not yet received our radio signals. The signals will not reach them until the 25th century. Any response cannot arrive here until the 30th century at the earliest. Any physical visit in response to our detected signals cannot occur for at least 1,000 years. This is not a pessimistic assessment, it is arithmetic. The speed of light means that detection and response are separated by years or decades or centuries, depending on the distance involved. Physical visits are separated by these same timescales, plus the additional transit time of any vessel that travels slower than light. The idea that an alien civilization might detect our signals and send a ship that arrives within a generation is only possible if they were already very close, within perhaps 10 to 20 light years, and already had the technology ready. There are about 30 to 40 star systems within 13 light years of Earth. None of them are known to have planets with the characteristics associated with complex life. This does not conclusively rule out life in any of them, particularly microbial life in subsurface environments that would not be detectable remotely. But on current evidence, the stars close enough for a response mission to arrive in a human lifetime are not the most promising candidates for civilization. Let us now talk about something that is genuinely strange about the physics of the situation, about the concept of the cosmic event horizon.
and how the accelerating expansion of the universe interacts with the speed of light to create a boundary beyond which everything is permanently inaccessible. The universe is expanding. Not just galaxies flying apart through space, the space itself is growing. And this expansion is accelerating, driven by something called dark energy, whose physical nature remains one of the deepest unsolved problems in physics. The acceleration of expansion has a specific consequence for the speed of light speed limit. Because space is expanding, distant objects are moving away from us, not only due to their own velocities, but due to the growth of the space between us and them. Beyond a certain distance, called the Hubble radius, currently about 13.8 billion light years, objects are receding from us at exactly the speed of light due to expansion alone. Beyond that radius, they recede faster than the speed of light, not because they are moving through space at superluminal speeds, which special relativity forbids, but because the space between us and them is growing at a rate that exceeds c. Light emitted by objects beyond the Hubble radius toward us must struggle against this expansion. For objects at precisely the Hubble radius, a photon aimed at us would effectively stand still. The expansion of space exactly cancels the photon's motion toward us. For objects beyond the Hubble radius, a photon aimed at us is actually carried away faster than it can travel toward us. Their light will never reach us. The practical radius within which we can ever receive signals, the cosmic event horizon, is not the same as the Hubble radius. Due to the way expansion has varied over cosmic history, the event horizon of our universe is approximately 16 billion light years. Any event occurring beyond that distance from us right now, any signal sent, any process that begins, will never, under any circumstances consistent with our current understanding of cosmology, be able to affect us. It is permanently and irreversibly beyond our cosmic horizon. And because the expansion is accelerating, this horizon is not static, it is shrinking. Not in the sense that we can see less of the universe over time in any practical sense, but in the sense that the set of events with which we could ever exchange causal influence is decreasing. Galaxies that are currently at the edge of detectability will eventually cross beyond the event horizon and disappear from our accessible universe permanently. In the very far future, tens of billions of years from now, the only galaxies visible from Earth, or from whatever inhabits this region of space, will be those in our local group, the Milky Way, Andromeda, and a few dozen smaller companions held together by their mutual gravity against the expansion of space. Everything else will have receded beyond the horizon. An observer in that future will see a nearly empty cosmos and will have no way to know that it once contained 2 trillion visible galaxies. We live in a cosmically privileged epoch in terms of observational reach. We can currently see across 46 billion light years. The universe is still young enough that most of it is visible to us. This will not always be true. What this means for the Fermi paradox and for interstellar contact is significant. Any civilization that exists in our local group but outside the Milky Way, in Andromeda for instance, is separated from us by approximately 2.5 million light years. Communication across this distance takes 2.5 million years per message. Any physical visit is essentially impossible on any timescale relevant to the civilization that sends the mission. These civilizations are, for all practical purposes, permanently out of reach, not just today, but forever. The universe has organized itself such that even civilizations within the same gravitational structure, the same supercluster, the same group of galaxies, are separated by distances that make physical contact essentially impossible, and communication a multi-generational undertaking. Let us now talk about something more concrete, about the specific numbers behind what is probably the most realistic near-term approach to interstellar exploration, and why it illustrates the speed of light problem in the clearest possible way. Breakthrough Starshot is a research program funded by the late Yuri Milner and endorsed by Stephen Hawking, announced in 2016. Its proposal? Accelerate gram-scale laser sail probes to approximately 20% of the speed of light using a ground-based laser array with a combined power of approximately 100 gigawatts, and send them to Alpha Centauri, the triple star system of which Proxima Centauri is a member, arriving in approximately 20 years. Let us look at the numbers honestly. The kinetic energy of a gram-scale probe at 20% of the speed of light is approximately 2 × 10 to the 12th power joules. This is equivalent to the energy released by about 500 tons of TNT. The laser must deliver this energy to the sail over a period of roughly 10 minutes of acceleration, which means a laser power of approximately 100 gigawatts sustained for that duration. For comparison, the entire electrical generating capacity of the United States is approximately 1,100 gigawatts. The Starshot laser array would require roughly 10% of current US generating capacity to operate for 10 minutes per launch. This is expensive, but not physically impossible for a sufficiently motivated civilization. The sail must be extremely thin, on the order of a few hundred nanometers, to achieve a mass-to-area ratio low enough for the laser pressure to provide useful acceleration. At this thickness, the sail material must also survive the laser intensity without being destroyed. The engineering challenges are real, but are being actively researched. The probe arrives at Proxima Centauri, or its vicinity, after approximately 20 years. Due to the speed, it cannot be decelerated. It will pass through the Alpha Centauri system in a matter of hours at 20% of the speed of light. During those hours, its instruments must capture as much data as possible. Then it is gone, continuing into interstellar space. The data it captures is transmitted back to Earth via laser communication. Traveling at the speed of light, the signal takes 4.24 years to arrive. Total elapsed time from launch to data receipt, approximately 24 years. A human generation. What can such a probe detect? Temperature profiles of planetary surfaces, atmospheric composition if the planet transits its star during the flyby window, magnetic field characteristics, surface reflectivity at different wavelengths, gravitational measurements. Not a comprehensive survey, not a landing, not a sample return. A brief flash of observation from a fast-moving platform transmitted back across 4 light-years of vacuum. This is what the state-of-the-art in realistic interstellar exploration looks like. A gram-scale chip on a laser-pushed sail, flying past its target in hours, returning data that takes 4 years to arrive, from a probe that cannot be steered, recovered, or followed up. The gap between this and a crewed interstellar vessel is not one of degree, it is categorical. The engineering that makes Starshot possible does not scale to human passengers. The energy scales, the mass ratios, the shielding requirements, the life support, the deceleration problem. Every one of these represents a different category of challenge when you add the requirement of keeping biological organisms alive and functional for decades of transit. Starshot represents humanity's genuine near-term frontier in interstellar exploration. It is impressive engineering, it is real science, and it is as different from the interstellar travel of science fiction as a message in a bottle is different from a transatlantic ocean liner. Let us now talk about the specific nature of how this constraint has shaped, and will continue to shape, our understanding of whether we are alone in the universe. The Drake equation, formulated by Frank Drake in 1961 for the first SETI conference at Green Bank, West Virginia, is a framework for estimating the number of communicating civilizations in our galaxy. It expresses this number as a product of factors: the rate of star formation, the fraction of stars with planets, the fraction of those planets that are habitable, the fraction on which life actually arises, the fraction on which intelligence evolves, the fraction that developed technology, and the average lifespan of a communicating civilization. Most of these factors remain poorly constrained. We now know that virtually all stars have planets, and that habitable zone rocky planets are common. Current estimates suggest there may be tens of billions of potentially habitable planets in the Milky Way alone. The fraction on which life arises is completely unknown. We have exactly one data point, Earth, and we cannot distinguish between life arises wherever conditions permit and life is extraordinarily rare even given the right conditions from a single example. What the Drake equation makes clear is that the answer to "are we alone" depends critically on one factor above all others: the average lifespan of a communicating civilization. If most civilizations that reach our current technological level last only a few centuries before destroying themselves, through war, ecological collapse, technological accident, then the galaxy may be effectively empty of currently active civilizations, even if life has arisen many times. The windows of simultaneous civilization would rarely overlap. This is called the Great Filter hypothesis, the idea that there is one or more steps in the development from simple chemistry to galaxy-spanning civilization that are passed by almost no one. The filter might be in our past, perhaps the emergence of complex cellular life, or of multicellular organisms, or of intelligence itself, is extraordinarily rare, in which case we may be among the very first civilizations and the galaxy is largely empty. Or the filter might be in our future. Perhaps the development of a civilization capable of long-term interstellar communication is routinely followed by its destruction, which would mean the silence of the sky is a warning, not merely a fact. The speed of light interacts with this question in an important way. If civilizations routinely last millions or billions of years, the galaxy should be detectably full of them by now, despite the speed of light constraint. There has been enough time for signals to propagate throughout the Milky Way many times over, and physical colonization at even a fraction of the speed of light could have filled the galaxy in a few 100 million years out of its 13 billion year age. The continued silence suggests either that civilizations are rare, or that they are short-lived, or that they go silent for reasons we do not understand. The speed of light does not resolve the Fermi paradox. It is one piece of a puzzle that remains genuinely unsolved. But it frames the puzzle in a specific way. Whatever the reason for the silence, it is not simply that the speed of light makes contact impossible. In 13 billion years, light speed signals could have filled the galaxy 100,000 times. If there were civilizations transmitting for billions of years, we would have detected them. The silence is not explained by the physics alone. The physics only sets the timescale on which contact is possible. The absence of contact on that timescale is the mystery. Let us now talk about something that has a specific and direct bearing on our daily experience, about the ways in which the finite speed of light already shapes our technology, our economy, and our moment-to-moment experience of a connected world. High-frequency trading. The financial markets of the 21st century operate on timescales of microseconds. Sophisticated automated trading systems execute thousands of transactions per second, exploiting price differentials that exist for fractions of a millisecond. In this environment, the physical distance between a trading firm's servers and the stock exchange matters enormously, not because of any human limitation, but because of the speed of light. A server located 1 meter from the exchange receives market data and can execute trades approximately 3 nanoseconds faster than a server located 2 meters away. This is not a trivial advantage in a system where nanoseconds determine profit. Trading firms spend millions of dollars moving servers into co-location facilities immediately adjacent to exchange servers, physically, literally as close as possible, specifically to minimize the light travel time between their computers and the exchange. The same principle operates at longer distances. Firms have laid dedicated fiber optic cables across the Atlantic Ocean, cables that follow the mathematically shortest possible path, rather than the existing cable routes that are slightly longer, to reduce transatlantic communication latency by milliseconds. The Hibernia Express cable from New York to London, completed in 2015, was routed to minimize length and reduce latency to approximately 59 milliseconds round trip. Its primary customers were financial firms for whom those milliseconds represented competitive advantage worth hundreds of millions of dollars. At transcontinental distances, the speed of light imposes irreducible minimum latencies. Los Angeles to New York, by the most direct possible fiber route, approximately 30 milliseconds one way. New York to London, about 28 milliseconds one way by the fastest available cables. New York to Tokyo, about 60 milliseconds one way. These latencies cannot be reduced by better technology, better cables, or better computers. They can only be reduced by reducing the physical distance that signals must travel. And since the locations of cities and exchanges are fixed, the latencies are fundamentally constrained. This is the speed of light operating not in the context of interstellar travel, but in the context of financial markets operating on your current street. The same constant, 299,792,458 meters per second, that makes travel to Proxima Centauri take tens of thousands of years at current speeds, also makes cross-continental financial communication take 30 milliseconds, regardless of the technology involved. The constraint is universal. It operates at every scale. The physics does not change based on how important the application is. Let us now talk about something philosophically important, about what it means to know about the universe from within the constraint of the speed of light, and whether that constraint is a tragedy or something more nuanced. There is a way of thinking about the speed of light limit that frames it as a deprivation, a prison wall separating us from the rest of the cosmos, making us prisoners on a single planet in a vast universe we can observe but never reach. From this perspective, the constraint is tragic. We can see the stars, we cannot touch them. We can detect the atmospheres of planets around other stars, we cannot go there. But there is another way of thinking about it. The speed of light is not merely a speed, it is the rate at which causality propagates. It is the speed at which one event can influence another. And a universe in which causality propagates at a finite speed is a universe in which local structure can exist, in which what happens here does not instantly affect what happens there, in which regions of the universe can evolve independently and develop complexity at their own pace without being overwhelmed by influences from across the cosmos. A universe in which causality propagated instantaneously, in which every event everywhere immediately influenced every other event, would not permit the stable local structures that allow complex chemistry and biology to exist. Atoms, molecules, cells, organisms, all of these require that local interactions dominate over distant ones, that the forces holding a molecule together are stronger than the noise from distant fluctuations across the cosmos. The finite speed of light creates the local isolation that allows complexity to emerge and persist. We exist because the speed of light is what it is. The isolation that frustrates our desire to explore the stars is the same isolation that allowed the chemistry of life to develop in the first place. This does not make the constraint less real. It does not bring Proxima Centauri any closer, but it situates the constraint within a larger physical context. The universe did not make a mistake by limiting signal propagation to 299,792,458 meters per second. That number is built into the structure of spacetime in a way that appears to be necessary for the existence of the kind of physics that produces galaxies, stars, planets, chemistry, and biology. We are, in a sense, beneficiaries of the very constraint we resent. Let us now talk about the specific question of what it would actually mean to detect a signal from another civilization, not as a thought experiment, but as a practical question about what comes next. Suppose SETI detects a signal tomorrow, unambiguously artificial, structured, containing information, originating from a direction near the star HD 40307, a K-type star approximately 41.8 light-years from Earth, which is known to host several planets, including at least one within or near its habitable zone. The signal was transmitted 41.8 years ago. It contains, once decoded, a compressed data package equivalent to a library's worth of information. Mathematical sequences, chemical descriptions, perhaps something that can be interpreted as biological data. What happens next? We can reply. Our reply travels at the speed of light and arrives at HD 40307 in 41.8 years. The civilization there receives it, prepares a response, transmits it. That response arrives at Earth 41.8 years after their transmission, approximately 84 years after our reply. A single exchange of messages takes 84 years. Within this constraint, information exchange is possible. Slow, asynchronous, multi-generational, but possible. We could learn about their mathematics, their physics, their biology, their history, their understanding of the universe. They could learn about ours. The exchange would be a correspondence, not a conversation. But correspondence has been among the most fertile modes of intellectual exchange in human history. The scientific revolution was built substantially on letters, documents that took weeks or months to cross Europe, carrying ideas that transformed civilization. The correspondence across 41.8 light years would take decades per exchange rather than weeks. But the principle is the same. Ideas, compressed into signals traveling at the speed of light, can cross the gap. What cannot cross the gap is matter, biology, physical artifacts, organisms. This is the honest picture of what interstellar contact actually looks like under the physics of our universe. Information exchanges over years and decades. Physical contact, if it ever occurs, over centuries and millennia. The romantic image of ships in the night, of civilizations meeting face to face, of a galaxy teeming with contact and trade and exchange, this is not what the physics supports. What the physics supports is a much quieter, much slower, much more patient kind of contact. Signals crossing the void. Minds touching across decades of light travel. The universe speaking to itself in the only language it permits. Electromagnetic radiation propagating at the maximum allowed speed, carrying meaning across distances that no material object could bridge in any civilizational time frame. And this, even this, would be transformative. Even a signal. Even proof that we are not alone, that somewhere around another star, another mind has solved the same equations, looked at the same sky, and decided to speak. The speed of light constrains the mode of contact. it does not prevent the fact of it. Let us now talk about what this all means for the specific question in this video's title, about whether aliens could ever reach Earth. The honest answer is, almost certainly not in any near-term sense consistent with the physics we understand. A civilization around any star within the sphere of our radio emissions, currently about 90 to 100 light-years in radius, could theoretically have detected us and could theoretically be building a response mission. But even at 20% of the speed of light, substantially faster than any propulsion system we know how to build, the journey from a civilization 50 light-years away would take 250 years. From 100 light-years, 500 years. From 1,000 light-years, 5,000 years. These are not journey times, they are civilization-spanning timescales. A mission launched today, aimed at Earth, would arrive when the civilization that launched it had either transformed beyond recognition or ceased to exist. Whatever arrived here would be the product of a civilization as distant in time from its launch as we are from medieval Europe. And the fuel problem remains. A crewed vessel capable of travelling at 20% of the speed of light and decelerating at Earth requires fuel mass ratios of hundreds to one, even under the most optimistic physical assumptions. The energy required to build and launch such a vessel is comparable to the total energy output of a star over significant fractions of its lifetime. A civilization capable of this is, by definition, operating at a scale of energy manipulation that we cannot currently imagine. Could such a civilization exist? Possibly. The Kardashev scale describes civilizations in terms of their energy use. Type 1 uses the energy of a planet, Type 2 uses the energy of a star, Type 3 uses the energy of a galaxy. We are currently at roughly 0.73 on this scale. A Type 2 civilization, harvesting a significant fraction of its star's output, would have access to energies sufficient for the kinds of propulsion that interstellar travel requires. But Type 2 civilizations would also be detectable. A civilization surrounding its star with structures to harvest stellar energy would alter the star's spectrum and reduce its infrared emission in characteristic ways, the so-called Dyson sphere signature. We have surveyed hundreds of thousands of stars specifically looking for this signature. We have found no confirmed examples. The silence of the Fermi paradox extends to the megastructures as well as to the radio signals. Whatever is out there, if anything, is not building the kinds of structures that would make interstellar travel energetically feasible and that would be detectable from Earth. This does not prove they do not exist. Absence of evidence is not evidence of absence when the evidence we are looking for is subtle or our search has been incomplete. But the combination of the energy requirements for interstellar travel, the fuel mass ratios, the timescales involved, and the absence of any confirmed detection of the kinds of civilizations that could overcome these barriers, converges on a single conclusion. Visiting Earth from another star is not merely difficult. It is so difficult, so energetically demanding, so time-consuming, that it appears to be beyond the reach of any civilization we have evidence for. The physics permits it, in the sense that it does not logically prohibit it, but the physics makes it so expensive that it may simply not happen at any frequency that would make it a part of Earth's history in any recognizable time frame. The space between stars is genuinely, almost incomprehensibly vast. The speed of light, for all its magnificence, is genuinely too slow to make that space easily navigable. Every alien civilization in the galaxy faces the same problem we face. The same mass ratios, the same transit times, the same trade-offs between velocity and fuel. The universe has given every civilization in it the same speed limit. And that speed limit, applied to the actual distances between stellar systems, makes the galaxy not a connected community, but a vast archipelago of isolated islands, each evolving on its own, each constrained by the same physics, each looking up at the same sky and facing the same silence. We look out at the stars. They are beautiful. They are real. Their light reaches us every night, crossing distances that dwarf anything in human experience. Let us talk about something that almost never appears in popular discussions of interstellar travel, but that matters deeply for understanding what the speed of light constraint actually implies: the concept of relative simultaneity, and what it means that there is no universal present moment connecting us to other civilizations across the galaxy. Our intuition tells us that right now, as you are reading this, there is a single present moment that encompasses the entire universe. That somewhere around Proxima Centauri, events are happening right now, simultaneously with this moment, and that right now there and right now here refer to the same cosmic instant. Special relativity says this is wrong. Not approximately wrong, precisely, fundamentally wrong. Simultaneity is relative to the observer's state of motion. Two events that are simultaneous for one observer are not simultaneous for another observer moving relative to the first. Both observers are correct within their own reference frames. There is no privileged reference frame from which the true simultaneity can be determined, because the laws of physics are the same in all inertial reference frames, and there is no experiment that can identify a state of absolute rest. The consequences of this for thinking about other civilizations are profound and rarely examined. When we ask whether there is, right now, intelligent life somewhere around another star, the question does not have a well-defined answer. Right now around Proxima Centauri is not a fixed point in spacetime that we can point to. It depends on our velocity. A person walking east asks about a different set of events right now at Proxima Centauri than a person walking west, even though the difference is tiny in practice because walking speeds are so far below the speed of light. For observers moving at substantial fractions of the speed of light relative to each other, as a hypothetical interstellar traveler would be relative to Earth, the disagreement about which events are simultaneous becomes significant. A traveler heading toward Proxima Centauri at 90% of the speed of light would define right now at Proxima Centauri as a different set of events than a stationary observer on Earth. The difference could amount to years. This is not a philosophical puzzle without practical consequences. It means that the concept of two civilizations existing at the same time becomes ambiguous at interstellar distances. We exist. Some civilization around another star might exist. But whether we exist simultaneously in any observer-independent sense, whether our histories overlap in cosmic time rather than merely in the light cone structure of space-time, is not a question with a definite answer. The universe does not have a universal clock. It has local clocks, each running at their own rate, depending on velocity and gravitational potential. The cosmic present that we imagine as the backdrop against which all civilizations live their lives simultaneously is a fiction. A convenient fiction that works perfectly well for everyday life on Earth, but breaks down fundamentally at the scales where interstellar civilization becomes relevant. This deepens the isolation imposed by the speed of light. We are not merely physically separated from other civilizations by distances that light takes years to cross. We are temporally separated in a sense that makes even the concept of contemporaneity, of existing at the same time, observer-dependent and therefore ambiguous. Let us now talk about something specific and currently active in physics that is relevant to the question of whether faster-than-light travel might ever be possible, about the experimental tests of general relativity and what they say about the malleability of space-time. General relativity describes gravity not as a force, but as the curvature of space-time caused by mass and energy. The more massive an object, the more it curves the space-time around it. Objects that appear to be moving in straight lines through curved space-time are actually following the straightest possible paths, geodesics, through that curved geometry. This framework has been tested to extraordinary precision. The precession of Mercury's orbit, predicted by general relativity and not explicable by Newtonian mechanics, matches the theory to better than 1 part in 1,000. The deflection of starlight passing near the Sun, first measured during the 1919 solar eclipse, matches the general relativistic prediction to within observational uncertainties. Gravitational time dilation, the slowing of clocks in stronger gravitational fields, is measured continuously by GPS satellites and corrected for in their operation. The expansion of the universe, the existence of black holes, the propagation of gravitational waves at the speed of light, all of these are predictions of general relativity that have been confirmed by observation. The theory is extraordinarily well verified, and, within the framework of general relativity, both wormholes and the Alcubierre warp metric are mathematically valid solutions. They do not violate the equations. They are, in the technical sense, consistent with the theory. But general relativity also predicts the specific conditions required for these solutions to exist. And those conditions involve the stress-energy tensor containing regions of negative energy density. The equations require that the exotic matter or energy maintaining these configurations exert negative pressure, and that its energy density be negative in the sense that matters for the spacetime geometry. The quantum field theory vacuum, the lowest energy state of quantum fields, does have negative energy density relative to some reference states in the form of the Casimir effect. Two uncharged conducting plates placed very close together in vacuum experience an attractive force because the quantum vacuum between them has fewer available modes of oscillation than the vacuum outside, resulting in a net inward pressure. The energy density of the vacuum between the plates is effectively negative relative to the outside. This is real. It has been measured. It demonstrates that negative energy density exists in nature, at least in specific quantum geometric configurations. The problem is quantitative. The Casimir effect produces negative energy densities of extremely small magnitude in geometrically specific situations. The negative energy required to hold open a traversable wormhole or create a stable Alcubierre bubble is many orders of magnitude larger. Estimates range from stellar mass equivalents to planetary mass equivalents, depending on the specific configuration, even after theoretical work has reduced the original estimates. The gap between the observed Casimir effect and the required exotic matter for a usable warp drive or wormhole is not a factor of 2 or 10 or 1,000. It is an almost incomprehensible number of orders of magnitude. Whether physics permits producing exotic matter at the required scale is unknown. No mechanism for doing so is suggested by current theory. The Casimir effect demonstrates that negative energy is not categorically forbidden, but it does not in any way suggest that it can be produced at scales that would be relevant for propulsion. The honest summary: within general relativity, faster-than-light travel is not logically impossible. It requires exotic matter. Exotic matter of a small kind demonstrably exists. Whether exotic matter of the kind and scale required for actual FTL propulsion can exist or be created is an open question in fundamental physics, but one for which current theory gives no positive indication. Let us now talk about something that is more accessible and more immediate, about what the scale of the universe actually feels like when you try to hold it in your mind, and why our intuitions about it are systematically, reliably wrong. The human brain evolved to navigate a world where the longest distance a person was likely to travel in their lifetime was a few hundred kilometers. The timescales that were relevant to survival were fractions of seconds to years. The fastest moving things we dealt with were animals and projectiles, speeds measured in tens of meters per second at most. Our intuitions about distance and time are calibrated to this scale, and they fail catastrophically when applied to the scale of the cosmos. Consider an analogy. Imagine you want to represent the solar system on a map at a scale where Earth is a centimetre across. At this scale, the Moon is 30 centimetres away, the length of a ruler. The Sun is about 12 metres across and sits about 1.2 kilometres from Earth. The outer edge of the solar system, the heliopause, where Voyager 1 now travels, is about 12 kilometres away. Now, at this same scale, where is Proxima Centauri? About 320,000 kilometres away, farther than the Moon is from Earth in real life. In a map where Earth is 1 centimetre, the nearest star is at the distance of the real Moon from the real Earth. This is the ratio. The solar system to the nearest star is roughly the ratio of a centimetre to the Earth-Moon distance, and the solar system, on the scale of human experience, is itself already almost incomprehensibly vast. The light travel time across the solar system is measured in hours. Another way to grasp the scale: if the Sun were the size of a white blood cell, roughly 10 micrometers, 1/100th of a millimetre, then the nearest star would be about 7 centimetres away. On this scale, you could fit 24 stars in a line across a typical dining room table. But the Milky Way galaxy, on this same scale, would extend about 700 metres, the length of 7 football fields, and the observable universe would span about 700 million kilometres, roughly 5 times the Earth-Sun distance. Our minds evolved to navigate rooms and fields and landscapes measured in meters and kilometers. We are simply not equipped to intuitively grasp the scale of interstellar space. Every analogy we construct, the grain of sand, the white blood cell, the map, distances, is an attempt to compress the incomprehensible into something the brain can process. And every attempt highlights the same fundamental fact. The gaps between stars are not merely large, they are large in a way that categorically exceeds anything our intuitions were built to process. And the speed of light, which covers the Earth-Moon distance in a little over a second and spans Earth's circumference 7.5 times per second, is still too slow by a factor of thousands to make these gaps crossable in time frames relevant to a human civilization. Let us now talk about the specific question of why the speed of light has the value it does. Why it is 299,792,458 meters per second, and not 10 times larger or 100 times smaller, and what this tells us about the structure of our universe. In physics, the speed of light in vacuum appears in 2 deeply different contexts. It appears as the constant in Maxwell's equations of electromagnetism, as 1 over the square root of epsilon naught mu naught, where epsilon naught is the permittivity of free space, and mu naught is the permeability of free space. These are properties of the electromagnetic field in vacuum. Maxwell derived the speed of light theoretically from electromagnetic constants measured in laboratory experiments with electricity and magnetism, before the connection to light was known. The coincidence between this calculated speed and the measured speed of light led him to conclude that light was an electromagnetic wave. It also appears as the fundamental speed of causality in special relativity, the maximum speed at which any influence can propagate, connected not specifically to light or electromagnetism, but to the structure of spacetime itself. That these 2 appearances of C, one derived from electromagnetism, one derived from the geometry of space-time, give the same value is not a coincidence. It reflects something deep about the relationship between electromagnetism and space-time. Maxwell's equations are already, in a sense, relativistic. They are consistent with special relativity without modification. When Einstein derived special relativity, Maxwell's equations were one of his motivations. The fact that electromagnetic wave equations have a fixed propagation speed in all reference frames was in tension with Newtonian mechanics, and special relativity resolved that tension by making the fixed speed fundamental. The value 299,792,458 meters per second is not a number that physics explains from more fundamental principles. It is, in modern physics, a definition. The meter is now defined as the distance light travels in 1/299,792,458th of a second. The speed of light is exactly 299,792,458 meters per second by definition. The measurement uncertainty has been moved into the definition of the meter rather than remaining in the speed of light. But the underlying physical constant, the relationship between the permittivity and permeability of free space, or equivalently the ratio of space to time in the geometry of spacetime, is a brute fact about our universe. Why it has the value it has and not some other value is not known. It is one of the fundamental constants of nature, like the fine structure constant, the gravitational constant, and the masses of elementary particles, whose values physics currently accepts as given rather than deriving from deeper theory. Some versions of the anthropic principle suggest that the value of c is constrained to be within certain ranges by the requirement that life, or at least chemistry, can exist. If c were much smaller, the energy of chemical bonds would be affected, and the chemistry of life might not work. If c were much larger, the relationship between mass and energy would change in ways that could alter nuclear and atomic physics. But these constraints are loose and speculative. We do not have a well-developed theory of which physical constants are consistent with life and which are not. The speed of light is what it is, and what it is catastrophically insufficient for the romantic vision of a galaxy connected by interstellar travel. Not because physics made a mistake, but because the universe we live in has the specific structure it has. A structure that permits chemistry, permits stars, permits planets, permits biology, and, as a consequence of all those same parameters, also makes the distances between those planets' stars nearly impassable in any time frame relevant to biological organisms. Let us now talk about something that is simultaneously an argument for pessimism about interstellar contact and an argument for deep optimism about our own significance: the specific nature of our cosmic position in time. We are, by all evidence, among the earliest technological civilizations in the history of the universe. The universe is 13.8 billion years old. Stars capable of hosting planets with the heavy elements necessary for complex chemistry, the elements formed in supernovae of earlier stellar generations, only began to be common a few billion years after the Big Bang. Earth formed 4.54 billion years ago, when the universe was already about 9.3 billion years old. But many stars formed earlier than the Sun. Many planets formed earlier than Earth. If life arises on a significant fraction of habitable planets, and intelligence follows eventually, then there could exist civilizations that are millions or billions of years more advanced than we are. The fact that these civilizations, if they exist, have not detectably colonized or transformed the galaxy, despite having had time to do so many times over, is the Fermi paradox. And the speed of light, while not by itself explaining the silence, constrains what colonizing the galaxy actually means in physical terms. Even at 1% of the speed of light, the rough speed of a sufficiently advanced civilization's automated probes, colonizing or surveying the entire Milky Way would take 10 million years. This is a long time by human standards. It is a small fraction of the galaxy's 13 billion year age. Civilizations that are 1 billion years more advanced than we are have had time to survey the galaxy 100 times over, even at 1% of the speed of light. The silence, in this context, is not explained by the speed of light. The speed of light constrains the timescale of colonization, but does not make it impossible on the timescale of cosmic history. The silence means either that there are very few, possibly no other civilizations that have existed long enough to colonize the galaxy, or that civilizations which reach our level routinely stop existing before doing so, or that the evidence of colonization is there and we are not recognizing it, or that civilizations reach a state in which expanding into the physical galaxy is not a priority, or not their mode of existence. All of these possibilities have profound implications. The first two are sobering. They suggest that either life is rare or civilization is fragile. The third is intriguing and somewhat unsettling. The fourth is philosophically rich. It suggests that sufficiently advanced civilizations may find the physical universe less interesting than some other mode of existence that we cannot currently imagine. None of these possibilities changes the specific physics of the speed of light, but they interact with it in ways that shape what the ultimate human relationship with the cosmos might look like. If we are genuinely early, if most civilizations are yet to come, arising on the planets now forming around the billions of stars that will still be burning billions of years from now, then we are participants in an early chapter of cosmic history. The galaxy is not full because it is mostly empty, not because life has come and gone, but because it has barely begun. In this scenario, the silence of the night sky is not the silence of a graveyard. It is the silence of a world before dawn, not empty, but early, waiting for the complexity that will eventually arise in it. And our moment here, this brief, improbable moment when a species on a small planet around an unremarkable star first developed the physics to understand its own cosmic isolation, is not a moment of tragedy. It is a first. The specific combination of early enough in cosmic history to be among the first and late enough to have the physics to know it, this is a privileged position in cosmic time, even if it is not a privileged position in cosmic space. We are not at the center of the universe. There is no center. But we may be at the beginning of something. And beginnings are not the least important moments in a story. They are often the most important. Let us now talk about what you can do tonight, specifically, concretely, with your own eyes and whatever optical instruments you have available, to experience the speed of light not as an abstraction, but as a physical reality that you can personally encounter. Go outside after dark and find a place where the horizon is visible in multiple directions. If you can find somewhere without significant light pollution, do so. Look at the moon if it is visible. What you are seeing is the moon as it was 1.28 seconds ago. The light that enters your eye when you look at the moon left the lunar surface 1.28 seconds before it reached you. If the moon were to suddenly change color right now, if its entire surface turned deep red, you would not know for 1.28 seconds. You would continue to see the old moon for more than a second after it had already changed. This is not metaphor, this is measurement. The distance to the moon divided by the speed of light gives 1.28 seconds. Every time you look at the moon, you are looking 1.28 seconds into the past. Now find Jupiter or Saturn, if either is above the horizon, a steady, non-twinkling point of light, brighter than the stars around it. Jupiter is currently between 588 and 969 million kilometers from Earth, depending on where both planets are in their orbits. The light you see from Jupiter left that planet somewhere between 33 and 54 minutes ago. You are seeing Jupiter not as it is, but as it was when that light was emitted, nearly an hour ago. Now look at the brightest stars. Sirius, the brightest star in the night sky, is 8.6 light-years away. The light reaching your eyes from Sirius left that star 8.6 years ago, in 2016. Whatever is happening at Sirius right now, whatever events are unfolding in that stellar system in this moment, you will not know about for 8.6 years. There is absolutely nothing you can do to learn about it faster. Canopus, the second brightest star in the sky and visible from southern latitudes, is about 310 light-years away. The light from Canopus reaching your eyes tonight left that star around 1715 CE. Isaac Newton had just published his Principia Mathematica about 28 years earlier. The American colonies were decades from declaring independence. When you look up at the night sky, you are not seeing a snapshot of the present universe. You are seeing a temporal collage, each star contributing light from a different moment in the past, all arriving at your eyes simultaneously, all presenting themselves as the night sky right now, when in fact, each one is a message from a different chapter of history. The nearest star visible to the naked eye from mid-northern latitudes other than the Sun, Alpha Centauri, visible as a bright star in the southern sky from locations below about 30 degrees north, is 4.37 light-years away. The light you see from it tonight left that star in late 2020. Whatever happened there since then is already history at that star, but the light carrying news of it is still en route. It has not arrived yet. It will not arrive for years. If you have binoculars or a small telescope and are in the southern hemisphere or at low northern latitudes, you can find the Andromeda galaxy, M31, as a fuzzy oval patch of light in the constellation Andromeda. The light from Andromeda reaching your eyes tonight has been travelling for 2.537 million years. It left that galaxy when our ancestors were not yet anatomically modern humans, when Homo habilis and early Homo erectus walked in East Africa, without fire, without language in any modern sense, without any of the cultural complexity that defines our species. The photons entering your eye when you look at Andromeda have been travelling through intergalactic space for longer than our genus has existed. This is the speed of light as a personal, sensory, immediate experience. Not an abstraction, not a number, a thing that is happening to your eyes right now as you look at the sky. Every photon arriving with a built-in timestamp, carrying information about a moment in the past that is further away the further you look. And none of those photons, however old, however far travelled, however long their journey, brings us any closer to physically crossing the distances they crossed. They arrive here. We cannot follow them back. That is the specific poetry of the constraint. Light crosses the universe freely in all directions, carrying information, filling our telescopes with the history of the cosmos. Matter, including the matter that makes up living organisms and civilizations, cannot follow at anything like the same pace. We are surrounded by messages from the universe. We can read them. We are learning to read them better every year as our instruments improve. What we cannot do is reply in any time frame that would constitute a conversation rather than a multi-generational exchange of letters. But we can read. We can understand. We can build models of what the universe is and how it works, and what else might be out there. Models accurate enough to calculate the positions of planets centuries in advance, to describe the nuclear reactions in stars 100 million light-years away, to reconstruct the first moments of the universe from the radiation that still fills all of space from that original event. The speed of light is a prison wall, and from within that prison, through instruments made of mirrors and lenses and electronics, we have mapped the structure of the observable universe out to 46 billion light-years. We have found the specific signatures of chemistry that suggests, not confirms, the possible presence of biological processes on worlds we cannot visit. We have detected the ripples in space-time caused by black holes merging more than 1 billion light-years away. We are confined to one small planet around one ordinary star in one of 200 billion galaxies, and we know this. We know the structure of the prison. We understand the physics of the walls. We can measure the distances we cannot cross. This is not a small thing. This is extraordinary, and they are very, very far away. Go outside tonight. Stand still for a moment. Look up. The stars that you can see on a clear night, the familiar ones, the ones that have been in the sky for all of human history, each one of them is a sun. Most of them larger than ours, many of them older, many of them surrounded by planets. And every single one of them is separated from us by a distance so vast that the fastest thing in the universe, the thing that crosses Earth's circumference 7.5 times per second, the thing that reaches the moon in 1.28 seconds, the thing that crosses from the sun to us in 8 minutes, takes years to cross. 4 years to the nearest one, 8 to Sirius, over 400 to the North Star. The light arriving at your eyes right now from those stars has been traveling for years, decades, centuries. It left those stars before you were born. Some of it left before your grandparents were born. Some of it left before the civilization you are part of existed in any recognizable form. And the distance that light crossed to reach you, that gap between your eye and the source, is the same gap that makes interstellar travel not merely difficult, but categorically, physically, fundamentally overwhelming. Let the numbers speak plainly. The nearest star, 40 trillion kilometers. Our best probe, traveling for nearly 50 years, has covered about 0.002% of that distance. A gram-scale laser sail, the most ambitious interstellar mission concept currently being seriously developed, would take 20 years to make the crossing and could not stop, could not return, could not carry anyone. A crewed ship. A real ship carrying people capable of decelerating at the destination so that its passengers could step out onto a new world. To travel at 20% of the speed of light, fast enough to reach Proxima Centauri in about 20 years, carrying a useful payload and fuel for deceleration, the fuel-mass ratio required under the most optimistic physical assumptions, approaches 100 to 1. 99% of the launch mass is fuel. For a crew module of 100 tons, you need roughly 10,000 tons of antimatter. The entire world produces a few dozen nanograms of antimatter per year. To go faster requires more fuel. Always more fuel. Exponentially more. The curve does not flatten, it steepens. The speed of light is 299,792,458 meters per second. This number is not the result of a design choice that could have been different. It is the speed at which causality propagates, the rate at which one event can influence another, written into the structure of spacetime itself. A universe with a different value of this constant would be a universe with different chemistry, different physics, possibly no atoms, possibly no stars. We exist because the constant has the value it has. the same value that makes the stars unreachable. The building blocks of us required this number. The isolation that comes with it is the price. Now consider what this means for the question that underlies everything we have discussed tonight. If any civilization exists around another star, close or far, simple or vastly advanced, it faces the same equations, the same mass ratios, the same transit times, the same trade-off between speed and fuel that scales exponentially as velocity approaches c. A civilization that is 1,000,000 years more advanced than we are has had 1,000,000 years to develop better physics, better engineering, better technology. But the equations of special relativity do not improve with development.
The Tsiolkovsky equation is not a first-generation approximation that future physics will supersede. It describes a fundamental relationship between mass, velocity, and energy that holds regardless of how the energy is produced or how the fuel is structured. There may be exotic physics, wormholes, warp metrics, configurations of negative energy density that circumvent these constraints. These possibilities are real mathematics applied to real general relativity, but they require exotic matter that has never been observed at any relevant scale. The gap between the Casimir effect, the only observed negative energy phenomenon, and the exotic matter required for a traversable wormhole or a stable warp bubble is not an engineering gap. It is a gap in fundamental physics. We do not know whether it can be bridged. What we do know is that no civilization has arrived. No signals with unambiguous artificial structure have been detected despite decades of searching.
No megastructures blocking starlight in the ways that stellar energy harvesting civilizations would produce have been found in surveys of hundreds of thousands of stars. The night sky is silent in the ways that a galaxy full of technologically active interstellar civilizations would not be. The silence could mean many things. Life might be rare. Civilizations might be short-lived. They might exist in forms or communicate in modes we are not yet equipped to detect. They might be there, waiting, watching, for reasons we cannot guess. But the silence is consistent with the most straightforward reading of the physics. Interstellar travel is so difficult that even civilizations that exist, even civilizations far more advanced than ours, may simply not do it. Not because they lack the will or the intelligence, because the universe built a wall between the stars so high that crossing it is, in practice, beyond reach for any civilization operating within known physics. We are not alone because we are unworthy. We are not isolated because we are forgotten. We are isolated because we live in a universe where the speed of causality, 299,792,458 meters per second, is simultaneously fast enough to carry light across the solar system in hours, and too slow by many orders of magnitude to make the gaps between stellar systems navigable in any civilizational time frame. The speed of light is the fastest thing there is, and it is not fast enough. That is the loneliest fact in all of physics. But now, here is the thing that transforms that loneliness into something else, something that I want you to hold on to as you look up at the night sky. We know this. That is not a small statement. It is an extraordinary one. We are a species that has been on this planet for perhaps 300,000 years. We have had writing for about 5,000. We have had anything resembling modern science for about 400. We have had the specific theory, special relativity, that explains the speed of light limit for about 120. In those 120 years, starting from Maxwell's equations and Einstein's 1905 paper and the experimental physics that followed, we have arrived at a complete, quantitative, experimentally verified understanding of why the stars are unreachable. We have measured the speed of light to better than 1 part per billion. We have used it to build GPS systems that correct for relativistic time dilation to keep their clocks synchronized. We have detected gravitational waves, ripples in spacetime traveling at precisely the speed of light, from black holes merging over 1 billion light-years away, confirming the theory that describes our cosmic prison with extraordinary precision. We are confined to one small world around one ordinary star, and we have mapped the structure of the confinement. We understand the physics of the walls. We know why they are where they are and how high they extend. The stars that you are looking at tonight, you know what they are. You know that they are suns. You know their approximate distances. You know that the light from them took years to reach your eyes. You know that if something happened there today, you could not know about it for years. You know that you could not go there in a lifetime, or in many lifetimes, with any propulsion system that physics permits. You know this because a sequence of curious people, Maxwell, Michelson, Morley, Einstein, Minkowski, Hubble, Sagan, thousands of others, spent their lives working out the nature of the universe we live in and sharing what they found, and that knowledge has been passed to you through the culture you were born into. This is what it means to be a technological civilization. Not just the ability to build things, but the ability to understand the context we exist in. To look at the night sky and know, rather than just wonder, what it contains and what it means. The speed of light is too slow for interstellar travel, and we know that. We can calculate it, we can test it, we can state with confidence what is possible and what is not, and why, in precise, quantitative terms. That knowing does not eliminate the distance. The stars are still 40 trillion kilometers away at their nearest. Nothing we know will change that tonight. But there is something in the knowing itself that is worth sitting with. The universe is not indifferent to whether we understand it. The universe does not have preferences. But we are not indifferent to whether we understand it. And the understanding we have built, imperfect, incomplete, still evolving, but genuine, is one of the most remarkable things that has ever happened on this planet. Look at the sky. Those points of light are not decorations. They are not the ceiling of a dome. They are suns, other suns, most of them with planets, many of them with something to offer, if only the physics allowed us to reach them. They are separated from us by distances that make the speed of light insufficient. That makes any ship we could build take longer to reach them than our civilization has existed. That creates a silence in the night sky that is consistent with the most natural reading of physics, that interstellar travel is so hard that perhaps no one does it at all, that the galaxy may be a vast and quiet place of isolated islands, each evolving on its own. But every photon from every star that reaches your eye tonight crossed that distance. Light makes the crossing. It always has. For billions of years, light from our sun has been traveling outward through space, reaching other stars, potentially illuminating, however dimly, other worlds. And light from those worlds has been traveling back, crossing the void, reaching Earth, carrying information. We are beginning, just beginning, to read that information, to detect the chemical signatures of atmospheres, to find the planets, to look for the signs of biology in the spectral fingerprints of distant worlds. We cannot go to them, but we can look, we can understand, we can know. That is what we are, not travellers, not yet, perhaps not ever, not between the stars, but watchers, readers of light, translators of the universe's most fundamental message, which is simply this: we are here, and so is everything else, and the space between us is filled with light that carries the history of it all. Go inside. But look up once more first. Whatever is out there, whatever exists around those stars, whatever has existed, whatever may one day exist, The light from those places is crossing the void right now. Some of it is reaching your eyes in this moment. The universe is communicating, constantly, in the only language it has. We are getting better at listening.